Alright, subscribers, glad you can join me because today we are going to be talking about thermochemistry equations. Now, this stuff is hot or cold because we are dealing with chemical equations that look specifically at the heat transfer involved in chemical reactions. So, what we're going to be doing here with 16.3 notes, our objectives are going to be, number one, be able to write thermochemical equations for chemical reactions in other processes. Number two, describe how energy is lost or gained during changes of state. And then number three, be able to calculate the heat absorbed or released in a chemical reaction. So we start out here with the definition of a thermochemical equation. And so thermochemical equations are simply defined as a balanced chemical equation that includes the physical states of all reactants and products and energy changes. So let me pause the video and write that down. All right, so there is that written definition. Now, what usually happens here is these thermochemical equations, they are expressed as the change in enthalpy, or delta H, which I will again define as change of enthalpy. Simply put, enthalpy is we are looking at the change of heat. Now, there are two types of thermochemistry examples or thermochemistry equations, and it all depends on if heat is lost or gained. So, number one, we have exothermic reactions. And so in exothermic reactions, we have heat that is lost. So when we write the equations, one example we have is iron, solid iron, combining with oxygen to produce iron 3 oxide. Now, this process right here is going to have a delta H with a negative 1,625 kilojoules of heat. So what happens here is this. The big difference between a regular chemical reaction and a thermochem reaction is this. This part right here that I have highlighted or I just went over is the exact same. It's balanced. There's states of matter. There's subscripts, coefficients. All of that jazz is the same, except we have just a slight difference here. In a thermochemistry example, we include this delta H, or change of enthalpy or heat, in this particular example. Now it's negative because heat was lost. Our other example is if heat is gained, and that is an endothermic reaction or equation, if we want to be specific there. So in an endothermic reaction, heat is gained, and when I say heat is gained or heat is lost, I mean by the system, by the chemical reaction that is happening. So an example of this is ammonium nitrate, NH4NO3, that decomposes or is dissolved in water and breaks down to ammonium ions and nitrate ions. Now, if I've ever done this or if I've ever made this solution in class right before class and you feel that beaker feels cold. And it feels cold because this stuff right here, to break down, this solid, to break down into these two things, it had to take heat away from the universe or from the surroundings. And so the Delta H is positive because heat goes into that process, and it gets a positive 27 kilojoules. Again, heat is gained by the system. So we have three things that we need to look at here, and they all deal with molar. So we are going to revisit that concept of the mole, and they all have to deal with heat exchange. So mole and heat exchange. Now the N value here, the N word, is a little bit different here on each of the very ends here. So we start out here with the molar enthalpy of combustion. So the molar enthalpy of combustion is defined as the enthalpy change for the complete burning of 1 mole of the substance. All right, so there is the written definition. And for molar enthalpy of combustion, again, how they do this or how they get numbers is they actually take 1 mole of a substance and they burn it, and they can calculate the heat exchange, the enthalpy of that particular process. Now, this stuff right here for the molar enthalpy of combustion, the symbol for it is delta H for change of enthalpy of combustion. So how we abbreviate combustion, right below that delta H, rewrite COMB, C-O-M-B, for combustion. Whenever you see that, that is dealing with what we just defined up top here. Now, the molar heat of vaporization, the next term down, is defined as the amount of heat required to vaporize 1 mole of a liquid substance. All right, so there is the written definition of the molar enthalpy of vaporization. Now, a couple of points to make here. Number one, the symbol that we use for this particular process is delta H, again, change in enthalpy, but this time here we put vape, delta H of vaporization. Number two, the second point that we need to make here is that a phase change occurs. A phase change occurs, and then vaporization. Think about boiling water. That is taking liquid water into vapor water. So what we have to think about here, this third thing, is this. The third thing with vaporization is that delta H is positive and endothermic. Positive and endothermic. So we had to put heat into a particular substance, a liquid, to make it or produce it into that vapor phase of matter. Now, the third thing that we're going to talk about down here is the molar enthalpy of fusion. Now, the molar enthalpy of fusion is defined as the amount of heat required to melt 1 mole of a solid substance. All right, there's the written definition. And again, 3 points to make here for the molar enthalpy of fusion. Number one, the symbol notation that we use for this process is delta H of FUS. That stands for fusion. Number two, just like we had above, number two, we had a phase change occur. And that's because we go from a solid to a liquid. Think of ice melting. And then number three here, once again, we have a positive delta H. And again, a positive delta H. If we think like a thermochemist, we have an endothermic possibility or an endothermic process that is occurring. All right, so we've gone over some of these definitions, and now we can apply a little bit of this information that we used here. So if we go over to page number 2, you will see that you have this chart. And on it, we are dealing with the phase change for 1 mole of water. So this is the phase change for 1 mole H2O. And so as 1 mole of H2O goes through this process, there is either going to be heat added to or taken away from water. So let's start down here with solid. Solid water, solid H2O, is just simply ice. And so as solid water goes to liquid water, what happens is this. We get a delta H process of fusion because we are melting this particular ice. And this delta H of fusion is a positive 6.01 kilojoules. Again, that's for exactly 1 mole. We have to, in 1 mole of water, we have to put in 6.01 kilojoules of heat to go from solid to liquid. Now, if we keep heating that liquid water up, eventually it's going to go to the gas phase or the water vapor phase. And what we would have to do, we would have to have a change in enthalpy of delta H of vaporization because the liquid water is vaporizing to, or we would have to use 40.7 kilojoules to get that 1 mole of liquid water into gaseous water. Now, there's a lot more energy used in this step from liquid to gas because those molecules, those atoms, are going really far apart. They're breaking all of those hydrogen bonds. They are breaking away from one another and becoming really far apart. If we go through the reverse process, what happens here? If we take 1 mole of gaseous water vapor and we cool it down, what we are going to do is this. We are going to condense gaseous water to liquid water. So the abbreviation for condensation is COND. That stands for condensation. Now, because we went from a gas to a liquid, we removed heat. So this symbol right here becomes negative, and we remove the same amount of heat we added to go from this step to this step. So we have a negative 40.7 kilojoules. Now, if we keep cooling that liquid water, we put that 1 mole of liquid water in the freezer, eventually this thing is going to freeze. And so what we get here is this. We get liquid water to become a solid. So we put delta H of the solid equals the negative amount of heat that we have to remove. So again, negative because we have to remove it, and that is 6.07 kilojoules. So phase change we've talked about here. We talked about it right before first semester break. We can incorporate that into this business here of what we just talked about. Now, what we can also do is a problem. So you have this problem here as well, but what we have is a bomb calorimeter. Now, a bomb calorimeter isn't as explosive as you might think, but it's a really controlled calorimeter where we have no or very, very limited exchange of the outside universe, the heat interactions there reacting with our substance or our process that's occurring. So it's a very, very controlled experiment. Anyways, we have this reaction right here that's listed. We have it occur and plenty of oxygen, but we have 54 grams of glucose, this stuff here I'm pointing at. We have it produce this much heat, or what we're trying to find out, I should say, is we want to know how much heat is in this 54 grams of glucose. So what we have to do some thinking. This is a thermochemical equation because it gives you delta H, which it's negative, so that means it's an exothermic reaction. That means heat is given off when this reaction occurs. The other thing is this. You will always have it given to you as kilojoules. This is how many kilojoules was released in this process. Now what I like to do, and it's not 100% correct, but what I like to do is this. I like to say, hey, this is going to be kilojoules per mole. Now again, you'll never get this per mole process, but if you think about this as per mole, kilojoules per mole, it's going to make life a whole lot easier when we go to solve this problem. So what we need to do is this. We need to take our amount in grams of glucose, and we first need to convert it to moles. And that comes back to this process right here. So we have 54 grams of glucose, and we convert it to moles. Again, diagonals cancel, so we end up with grams of C6H12O6 on bottom, and then on top we put moles of C6H12O6. Now our gram to mole, our molar mass, is listed right here. This 180 number, the big number, is always associated with grams, so we put 180.16 right there with grams, and then on top, that's for every 1 mole. Now we get to this process here. We have to do some thinking because this is the amount of heat released per 1 mole. And so what we have to do is this. We've converted to moles of glucose. And so what we have to do now is we have to convert to how much heat evolved when this amount of glucose was reacted through this bomb calorimeter. So in this value, this is important here, for every 1 mole of this C6H12O6, there is negative 2,808 kilojoules per that mole. So on top here, we're going to write down this negative 2,808 kilojoules. And again, that is because we had 1 mole, and I should specify we had 1 mole of this C6H12O6. So what I do to go through this calculation is I insert these values into my calculator. So I take 54 divided by 180.16, and then what I do is I multiply it by negative 2,808. Now, what I get here is I get negative 841 and some change. And because I had 3 digits here, I'm going to round this to 3 digits. So my answer when I burn 54 grams of glucose is negative 842 kilojoules of heat. And that symbol is really important. So that means 842 kilojoules, because it's negative, is released, and that becomes my answer. All right, I hope you enjoyed another video and learned some more about thermochemistry in this particular video. And as always, make sure you subscribe.